Welcome to Science Simplified Network. In the structured world of organic chemistry, some rules are as old as the science itself, framing how chemists understand molecular stability and structure. One of those guiding principles is Brett's rule. This long-standing rule warns that double bonds at bridgehead carbons in bicyclic compounds are too strained to exist. For generations, it's been chemistry gospel, shaping the design and synthesis of countless compounds. But just recently, researchers have cracked open a new possibility, showing that Brett's rule can be defied under the right conditions. This breakthrough is creating waves and may lead to discoveries in pharmaceuticals, materials, and molecular design that once seemed like the stuff of science fiction. What is Brett's rule? Imagine a molecular structure like a suspension bridge, connecting 2 points over a valley. In a bicyclic compound, this bridge is a bridgehead carbon connecting 2 rings. Brett's rule has historically asserted that a double bond at this bridgehead point is simply too unstable, like trying to stretch that bridge too tightly without support. For a stable compound to form, double bonds were generally thought to be off-limits here. In a remarkable series of experiments, chemists recently achieved what was once deemed impossible: stable double bonds at bridgehead positions. Researchers successfully synthesized anti-Bredt olefins, ABOs, by applying a modified Kobayashi-type elimination reaction. They used silyl, halide precursors and a fluoride source to produce ABOs, which were then captured through trapping experiments. This method allowed for in situ generation of ABOs, followed by various cycloaddition reactions, e.g., 4+2, 2+2, 3+2, that confirmed the formation and reactivity of the highly strained ABO structures. Computational studies further validated the geometric distortions, twisting, and pyramidalization present in the ABOs, contributing to their distinct reactivity. This means that bridgehead carbons can, in fact, support double bonds without collapsing the molecule. This isn't just a theoretical curiosity, it's a revelation. For the first time, chemists have a green light to experiment with bridgehead unsaturation, opening the door to previously unreachable compounds. This discovery is essentially giving chemists new building blocks with which to innovate. The implications are profound. When rules like Brett's fall, they don't just make way for small changes, they create revolutions in how scientists think about molecule design. Here's why this matters. Brett's rule has long been a limiting factor in synthesizing certain cyclic compounds. With the potential to sidestep this rule, chemists can now create molecules that were previously impossible, potentially leading to compounds with novel reactivity and stability. Many drugs rely on the stability of cyclic compounds. By exploring bridgehead double bonds, chemists may design new drug structures with improved stability, target specificity, or bioavailability. This breakthrough could spark innovations in materials science, potentially leading to new materials that are stronger, more flexible, or possess unique electronic properties, like enhanced conductivity or optical responses. This discovery changes the way chemists understand molecular strain and stability, prompting further research into other impossible molecular configurations. This breakthrough doesn't just challenge a chemistry rule, it opens up an entirely new field of inquiry. Imagine molecular engineers designing custom bridgehead compounds for use in next-generation electronics, or biologists developing drugs that specifically bind to certain proteins. Every new compound, every bend of the rule, could lead to real-world innovations that change lives. Brett's rule, for so long a rigid boundary in chemistry, now represents the starting point for a new era. Science, after all, advances most when it questions its assumptions and redefines what is possible. This discovery is a testament to the importance of pushing limits and asking, what if? In the coming years, researchers will likely dive deep into this newfound flexibility in molecular design, exploring compounds that Bredt's rule would have previously discouraged. With advances in computational modeling, spectroscopy, and synthetic techniques, chemists will be able to push the boundaries of what's achievable, potentially unlocking compounds with extraordinary, yet to be imagined properties. So, as we look to the future of chemistry, it's clear that the rule-breaking spirit of this discovery will inspire not just new compounds but new thinking. And who knows? The next breakthrough might be hidden in a molecule waiting to bend a rule or break one entirely. Stay tuned with us at Science Simplified Network for more updates on how the science of today is shaping the world of tomorrow.